First of all, welcome to our talk. As the title is already introduced and our names as well, I guess we just move on. And a bit about us. I'm Rahul. I'm an infra consultant here at Thoughtworks. Started off as a developer and then gradually moved on to what I like to say the dark side, which is into the world of containers, cloud, infrastructure, CI/CD, and so on. And my work involves a lot of business to tech translation. So I think that is the most important thing I've been able to learn apart from all the code and programming and all of it. And to describe myself a bit for people who can't see us on video, um, I have short hair. I'm wearing a kind of blue t-shirt, and people often say I look angry, but I can assure you that's not the case for the talk at least. So moving on, Katja.
Yes, hi. I am Katja. I'm a developer at Thoughtworks, and I have promised Rahul that as soon as I have figured out what my purpose in life or at work is, I will add it here. That is still a work in progress, as you can see. I have long hair, and yes, I'm a woman in my mid-20s. So let's talk a bit about why we're here. Rahul and I build on a project together. It's an infrastructure project. And we are building a platform on AWS. We have a lot of consumers that are supposed to get their own AWS account with all the infrastructure built in. When Rahul and I first started on this project, we were a very small infrastructure team that started with zero code written, which is somewhat of a rarity. And we were expecting to get a lot of consumers that wanted to onboard within half a year. So while working on this project for more than 1.5 years now, we noticed that we applied some strategies, and this is what we are talking about today. So here's a quick overview of the infrastructure product that this talk is based on. So we are developing. We are still developing this. We are still growing in terms of onboarding new consumers, and we are also still developing new features at the same time. We are building, again, on AWS, a small team with a growing number of customers. We have, we define our infrastructure as a product offering. And what we actually deliver is a pre-configured AWS account and some services to our customers. And then our consumers or customers can extend on the infrastructure that we provide them. So let's talk about some of the choices that we have made on our platform that this talk is not about, just to kind of have the baseline be understood, because it is somewhat important as the background information to be able to follow this. So on our platform, we have no manual operations. Everything that we commit in code, we write everything in code. And whenever we commit, it triggers a pipeline. We do not do anything via the AWS development portal or the UI. And we don't even apply Terraform manually from our laptops. So as I've already said, we have everything in code. We work in Terraform. Some of these examples will be in Terraform. However, the principles will still apply to no matter which language you write, or most of it anyway. So we also we work with continuous integration. We chose trunk-based development, and at least Rahul and I have bonded over coffee.
All right, then let's talk about infrastructure, this heavy and scary word. And what we're talking about is infrastructure platforms. And in my head, the goal of infrastructure is to serve or adapt to the needs of the customers, in which our case, which are developers and their own applications. Platforms as products that do this well naturally will attract more customers over time, get popular. And what started off as a very simple platform with a few resources, very simple code base, now has to deal with a lot of customers which have different requirements, different needs, different desires from the platform. And in meeting those demands from your varied set of customers, it's not uncommon for complexity to grow exponentially with each customer onboarding. It's not uncommon for infrastructure to become a beast, which ends up hindering the applications and the customers where it was meant to enable them. And this has a big domino effect, as we'll see. So, quoting from this friendly philosopher, ambiguity makes us fear change, and evading change inhibits growth. Now, this is especially true for the world of infrastructure, because the less you understand about the system you're developing, the code that is behind it, the more you will be afraid to make changes to that system, afraid to break stuff, afraid to do anything. And once you get to that point, we of course get slower. We'll think 10 times before doing anything to our system. And this really inhibits growth, not just of the product itself, but of your customers, and most importantly, of the people working on the product and the applications. So, what can we do to not reach this place? That is where software development patterns come into the picture, because the world of software has been moving really, really fast. There are paradigms like microservices, which have become now standard in the industry, and these place even more demands on infra platforms. So we can look to these design concepts or patterns, apply them to infrastructure to match applications in their agility and match our customers, support them in agile development. So that's the first one we'll start off with. That would be about single responsibility. A quick recap, what are we talking about? Single responsibility means a unit of your system does one thing and does that thing really, really well. So, how can that apply to infrastructure? Now, let's talk about some minions, right? So, any system would have units. What we want to have, or how we want to start a platform, is by having very small, loosely coupled units. Uh, if we talk about minions, one of them is playing a guitar, one of them is having a teddy bear, another one is just standing doing not much. And all of them have this boundary that you see, the colored circle. In terms of infrastructure, what this would mean is, let's say you have some sort of code that is living in a directory, might be a Terraform module, which we'll get to later. And importantly, this is being applied as one pipeline. It is independent and independently manageable and deployable. What this helps you to do to have small units to begin with is to gain confidence, because you're experimenting with new infrastructure. You get fast feedback. You can share knowledge about the new platform much smoothly with your team, and it lets you test much quicker and eventually get fast feedback about what you're doing. Now, as your platform starts to grow, you will realize that a few of these minions are becoming very, very talkative with each other. That's what we discovered with one of our systems. To make it specific, this was like a Kubernetes cluster where we broke everything down to begin with. Then we realized if we change one thing, another thing also has to be changed. They were not loosely coupled as we thought, but very, very interactive. The two minions were talking so much to each other and they wanted to break out of their boundaries. And as you can imagine, we could no longer contain them. So we had to bring them together. And this brings us to high cohesion, whereas we started from loose coupling. Now that they were together, they was of course enjoying each other's company. They were much more friendlier. They did not have to cross a wall to pass data amongst them, and it was a lot of fun for them. But as you can imagine, things got very noisy, a bit chaotic, and we were starting to reach that point from the first module of drowning ourselves in complexity. So, what can we do to help those matters? To begin with, this is where we take an example of Terraform, where we've decided a certain layout. We always have business use cases at the parent level, which are abstracted terms. These might have some configuration, some variable inputs, and just very simple instantiations of the function you want to call. Then we have modules, which within them, the files we have broken down are into technical functions. So those three minions that you see, each of them, even though they are in the same module, could reside in different files. This makes it more readable, and again, the benefits that I described about single responsibility, we try to preserve them still. And to conclude on this part of the concept, less is always more. We want to start with independent testable units, start small, gain confidence, and then compose into cohesive modules and make sure you make everything readable.
Okay. Another principle that we applied is the open-closed principle. So, and we applied this in infrastructure, but the open-closed principle also comes from software development. For us, it means that we aim to build modules. Aim to build small modules that have one use case, so that we may end up with a clear scope for our individual modules. So this is an anti-pattern, because I think personally that one of the best things about going to technical presentations is the opportunity to have some Schadenfreude when we see that we code that we ourselves would absolutely never write. So not this exactly, but this is the concept of a module that I wrote early on for permission management, which in the case of AWS means IAM roles. It heavily went against the open-closed principle, but back then I wasn't thinking about that. So let's explore what it was and why it was such an anti-pattern to clean and extendable code. So what we tried then was to centralize the entire creation of all IAM roles for any given account. What happened was that it had many, many conditional statements, and seeing the module call alone in any account did not tell you anything about the state of your account. You would have had to go hunting through separate files to find out which roles exactly would exist in this account, which goes against many of the upsides that come with configuring infrastructure as code in the first place, like the declarative nature. So what ended up happening was that it had to be extended and changed constantly. It was very complicated, and it just tried to do too many things at once. Also, since it was changed all the time, it had version changes, and it was really hard to integrate with new features. So I think one of the things that's easy to forget is that other developers will have to read and work with our codes many times during its lifetime. They will not have the same thought processes or the exact same background knowledge that we do. And the more clean and clear we can make our code, the easier it will be to fix bugs and develop features on top of it in the future. So looking at how we should be doing it, how we should apply the open close principle. So we have an example of this principle in our networking setup. What we realized was that we created our virtual private network, our VPC, and our subnets in a very simple module early on, and then just provided a variable. And that is it. That's all the module does. Its scope is so small that we never had any reason to touch it. And we wouldn't unless some syntax changes, but certainly not to develop a new feature. So what we do, however, do very regularly is extend our networking. We build things into the VPC and into the subnets, but we never change it. So to be able to do this, to be able to extend upon our module, we create other modules, other small kind of components that then query the data from this original networking setup. So here again, we see the diagram. We have a very simple module in the top, and then we extend upon it with other modules. Some of the one trade-off does come with this. We do have to share data somehow in Terraform and in a lot of languages, a lot of infrastructure languages. It is supported to query resources by name or tag, which does require hard-coded values. But with Terraform, we can also utilize remote state. which we will talk a bit more about later. And we use a parameter store or a database with a lot of our values. But these things come with permission handling, which can be complicated across accounts. But it's certainly better than having to constantly change one module and just making everything super complicated. So, yes, don't touch that module. As a conclusion, with the open close principles, we want to build small and specific modules that can be easily understood and extended. It eases our scaling our code over time, it improves mutability, and it reduces the probability that we introduce bugs into existing resources because it's just so simple to understand the scope of this.
Right. Next, let's look at what Iron Man is annoyed about. That brings us to a very simple concept that is known to most developers as second nature, and that is looping or iteration. In infrastructure, this is still not very prevalent as you may think, especially with a declarative language. And I'd like to call one example from our project where we provide services to our customers on the cloud. These services represent on-premise systems that our people on the cloud want to access. And as you can imagine, there are many services on-premise, a lot of them critical to the business of our customers. So we spent a lot of effort, wrapped up this functionality in a neatly scoped module, which you see on the left. And what we saw was with each module call that we made, or each time we instantiated this module, it added a block of code to our Terraform files, and all of them had hard-coded configuration right besides Terraform. Our code ended up looking like what you see on the right, and you can imagine if there are 50 such services with more growing, it became really, really huge. And if you even imagine that we wanted to add one input variable to the module call, how much change would this have to be made? Plus, if you need some output from each of these services elsewhere in your system, the interaction patterns are just way too complicated. But then Terraform introduced module loops, and that had a very positive impact on our code base. Instead of 50 or more module calls, we only had one module call, as you can see there, with this for each construct. What you passed into this for each was an external list. Whatever we had hard coded within the code base, we took it out, put it in a list sort of a structure into a different repo, which could be also controlled by our customers, but we'll get to that later. Now, what happened was our code base got reduced by 90% almost because you only had one module call. And if you had a new service call coming along, all you need to do was add a configuration to that list. Our automation would kick in and the rest is taken care of. Now, all this sounds very good, but if you were simply to make this change from the old design to the new design, you would disrupt your system because Terraform would destroy everything and then recreate the services based on your new code. And obviously, we want to avoid this. That brings us to the dreaded state in infrastructure. Now, to refresh what is a state, maybe declarative languages are more associated with it. It represents the single source of truth for your entire infrastructure system. Whatever changes you make through code, some persistence is stored in the state file. Different ways tools do this, but it's like reading your entire infrastructure system in a book. That's what it is. And what we had to do to not cause disruption with our earlier change is to do something called state surgery. Many of whom who have used Terraform might be familiar with this, but what does it mean? Is that you modify the state file directly in a very controlled manner so as to avoid disruption. Taking an example, what we had to do was run a command, Terraform state move, uh, the source, which was module.service1, to our new pattern, which was module.services, and within that, it was an index called service1. Now, when you're doing operations like this, there are some important points to consider. One is this is a risky operation. You have to consider how much benefit will you get from doing this out of your refactoring, and is it worth the risk to perform it. So you always have to consider risk versus reward. You have to do it responsibly. Uh, that means your team must have some practice of doing state surgeries, to have tested this in non-critical systems, and to know what the outcome is going to be before you actually perform it. You still do not want to do it manually by applying Terraform from your laptop. You want an audit trail, you want it to be automated. So obviously we do it in pipelines. And another trick you can use is a dry run or a pausing apply stage, where if you run that command, it does not do anything, it just shows you what it could do. And by using all these things, we were able to move or refactor our code without disrupting our customers. So to conclude on don't repeat yourself, design your modules in a way that they can be scaled, externalize instance configurations, leverage the power of your infra tool for iteration, and use state surgery responsibly.
So, talking a bit more about the networking that we were talking about, what were we extending? So when we first architected our networking design, we opted for an AWS endpoint service architecture. So don't be too scared, even if you're unfamiliar with the specific technology. We will abstract it. So in software engineering, dependency injection is a technique where one object supplies the dependencies for another object. A dependency is an object that can be used often as a service. So in application development, dependency injection is also often defined as the decoupling of the creation of dependent components, mutually dependent components. Now, Terraform modules have a form of dependency injection by default. Terraform encourages the flat modular code hierarchy and providing the dependencies as variables. However, we took it a bit further into this principle. So here on the slide, you see on the left side a shared services account, on the right side some consumer accounts. In an abstracted form, our problem statement was a potential one-to-many relationship where we had two highly interactive and dependent resources, which may or may not have been created at the same time, but need to share some data between them. In our project, we were designing our endpoint service architecture. We used module loops and conditionals to create a loose coupling strategy for these highly dependent components. So these two components are dependent. We have a one-to-many relationship. As you can see here, we have a parameter store that shares the data. These lines represent data having to be shared between them. And as we also can see, there's that one consumer account may not need to instantiate all the services on the left. And all of this enabled us to have some dependency injection. So here's a more hands-on example, a code example. We have a component A, which is what used to be on the left side of the screen just now. Here we have a for each loop. We load some config data from an outside source. And in component B, which was on the right side of the screen, we query the data from from the shared service and put it into our service name. So we use that value from the parameter store. And then we enable, we have a conditional statement where we load from outside which endpoints does the team need. So this is a separate repository that we load in, and therefore we have kind of this decoupled from the code base itself, and we don't need to hard code anything. So concluding on dependency injection, it promotes loose coupling, it provides flexibility and the reusability of code, it can speed up development, and it enables opt-in features where if you don't need everything from these shared services, you have the option to just instantiate the ones that you need. So we have spoken about these 4 principles and how we have applied them. We have single responsibility, open close principle. We have the dry, don't repeat yourself, and we have dependency injection. But what were the actual benefits that we saw for our project first? So we saw that in terms of speed, we had faster onboarding, we had faster and easier feature development and scalability, because our code was relatively clean and relatively easy to understand, but certainly better than it would have been had we not applied these principles. We had a higher quality of code. So what does that enable us to do? We have more flexibility. The maintainability of it is a lot easier, right? If you have syntax changes, you kind of have an easier time looking. We had improved code quality, and because of that, we had less tech debt creation. And then in our team experience, you can kind of also call this developer experience, but these principles also did kind of help our business people as well. So we had smoother onboarding. We had better knowledge sharing because we could spend more time talking about the concepts instead of talking about the implementation details because it was just so complicated. And also, frankly, it's a lot more fun to work on a clean code base that makes sense, because then you can make quick progress with cards, and it's just a lot more fun to develop on that. But of course, maybe our PO's favorite is that we have cost savings due to this. Clean code writing is cost effective because we just spend less time understanding old code and potentially rewriting existing solutions because they are just so complex, we can't use them or we can't even understand them. So all of that saves cost. And then for our consumers or our customers, we spend more time developing features because we spend less time maintaining. We were able to share some of our small modules because our consumers were trying to do the exact same thing, and we're like, oh, here's this very small package of code, there you go. And we are able to keep our features modern because we have a somewhat faster pace of development. Of course, agile principles also help with that. But all of the benefits that we have listed in one way or another lead to cost savings, either for our consumers or for our project. And business people in general usually love saving money. However, focusing on building quality and working infrastructure and taking the time to do so controlled and cleanly has also benefited our project in technical ways. It has enabled us to grow our platform very quickly with a relatively small team, especially in the beginning. And therefore, we were able to bring this infrastructure product to our customers and to be able to continuously do so and grow while maintaining it. So this is what we call the magic formula. Just a quick reminder in case you just tuned in later. We are trying to maintain several accounts, several AWS accounts for different consumers, all of them obviously having slightly differing needs. And we have now talked about this code, which is now beautiful and maintainable and super scalable. What we chose to do is we maintain only one repository that rolls out to all accounts. And the way that we are able to do that to supply the differing needs is the configuration that comes in here. This is separate files, and these are actually owned by our customers. They can change them how they need. And then we feed all of this into a pipeline, or many pipelines actually, and then some magic happens and we get our customers get their infrastructure. This enables us that, or not us, but our customers, that even small teams can onboard quickly just by adjusting a few configuration files that they own. And really what we have developed here is a self-service for infrastructure provisioning and changing your infrastructure. That our customers can control and that they can then build and extend on top of. Self-service. All right. Now we have a beautiful code base. Our customers control their configuration. We roll out through pipelines. But how do we actually orchestrate the deployment of one code base to several accounts?
So let's go deeper into the orchestration aspect of how the changes are actually propagating across customers, across environments. That's where the value stream map comes into the picture. And this is a concept where you can think of, you create some value or a change on the left hand side of your system. It progressively goes through several stages, and it is in a point that it can be deployed to your customer in prod if the gates pass. This is your typical CI/CD. So what we have is code and config, the magic formula Katja just spoke about, uh, getting first applied to a test account. This is a simulated version of our customer account, and a single piece of change gets tested here. Only if it is successful, then a fan out happens across our many customers, 1 to n, and it triggers their pre-production pipeline. If the changes are successful there, then it triggers the corresponding production pipeline for that customer. So then you have a serial relationship. In this way, when we have single responsibility modules, we have a pipeline per module, and we make a change. We get immediate feedback through this value stream map. And if it is successful, the change is deployed to all our customers across environments within minutes. And if we think about what happens, you have a new component in your product. Imagine this huge AWS account and you introduce a new service. All that is required after you've added a block of code for that is a new pipeline. And the rest is taken care of, as we'll see here. So how do you scale across customers and across all these pipelines? We have 1 to n customers. Each of those have a series of pipelines that you can see in the blue boxes. And let's say a new customer comes along, asks us to give us an AWS account. What has to happen is we just need a pull request. When we merge that pull request, a set of pipelines flow in, they trigger, they deploy individual units of our infrastructure code. And at the end of it, if everything is successful, you get a product, our AWS account as a product, delivered right to you without any additional effort.
And all of that together is how we have tamed the exploding complexity and manual work, or in other words, how we have tamed the infrastructure beast with minions.